Okay, so in this video, we want to talk about how to obtain information about a function from its derivatives. So until this point, we've been given a function f expressed algebraically and have used calculus to graph the function. We're now going to use the first and second derivatives of a function to obtain information about the graph of f. So an AP exam tip here, it's common to find questions on the AP exam that expect you to draw inferences about the behavior of the function f given information about its first and second derivatives. Now, here's where we have to be careful because we have an original function, the first derivative, and the second derivative. You have to be careful about which function they're asking you questions about and which function, the original first or second derivative, that they're giving you information from. So for this one, example 6 here, we want to um, do these 5 things here. So look at the conditions. A function f is twice differentiable on its domain, the set of real numbers. So we know it's differentiable, which means it's continuous, since the second derivative exists because it's twice differentiable. We know the first derivative is continuous. And they gave us the graphs anyway, so we have some information. So for part A, we want to determine the critical numbers of f. So since f is differentiable at all real numbers, f and f prime are continuous, and therefore the critical numbers occur when f prime equals 0. And so from the graph right here, we can see that that occurs at x equals -2 and x equals 0. So, or no, not 0. 3. So we conclude that -2 and 3 are the critical numbers. For part B, we want to know on what intervals is f increasing and when is f decreasing. So we can use the increasing decreasing function test and look for where f prime is greater than 0. That would be on the interval 3 to infinity, because this portion of the graph is positive. F prime is less than 0 on the interval -infinity to -2 and 2 to 0. Because right here, the first derivative equals 0, but it's negative before and negative between -2 and 3. So now how do we actually write our interval? Um, because the function is continuous, the original function for all real numbers, we can just summarize by saying f is increasing on the interval 3 to infinity. It's a closed interval. And it's decreasing on the interval -infinity to 3. Now, I know I included 3 in both intervals, but that's because the definition of increasing is from one point to the next. And so 3 is where the function's decreasing interval stops, and it's also where the function's increasing interval starts. Okay? So C, at what numbers x does f have a local minimum? So since f prime is negative for x less than 3 and positive for x greater than 3, by the first derivative, f has a local min at x equals 3. So local min since f prime changes from negative, we get some more space here, to positive at x equals 3. Okay. Now, f has no other local extrema because there's no other values where f prime changes sign. So part D, now we want to know where is f concave up and where is f concave down. So we're going to use the test for concavity and the figure or the graph of the second derivative. So because f double prime is positive on negative infinity to negative 2, so right here, and 4/3 to 0, or excuse me, 4/3 to infinity, we know that the function is concave up. And the second derivative is negative on the interval negative 2 to 4/3. So f is concave down on that interval. All right. And then the last question lists any points of inflection. So E, we have a point of inflection when the second derivative changes sign. Well, the second derivative changes sign at x equals negative 2 and x equals positive 4/3. So f double prime changes sign at x equals negative 2 and 4/3. So f has a point of inflection at negative 2 comma f of negative 2 and 4/3 comma f of 4/3. Now we don't know what the actual function is, so we can't actually determine the y values, but we can determine, we can write the notation for the points. Okay, so our next question that we want to go over concerns obtaining information about the graph of a function from numerical information. So we have a function f is continuous on the closed interval negative 4 to 7 and is twice differentiable on the open interval negative 4 to 7, except that x equals 6. Information about f, f prime, f double prime are given in the table. So we have a big table of values here, and then we're going to determine determine all this information. Okay, so it's important to know this given information about a function being continuous and the intervals and all of that. So part A, identify the intervals on which f is increasing or decreasing. So we know f is continuous from negative 4 to 7 and differentiable, except that x equals 6. So we can use the increasing decreasing function test. So since f prime is greater than 0 on negative 4 to negative 2, negative 2 to 0, and 6 to 7, f is continuous. So f is increasing on negative 4 to 0 and 6 to 7. Now I can include negative 4, or I can include negative 2 on this interval because the first derivative is still positive anyway on that interval. Okay, so part B, when I identify, or no, we got to do when f is decreasing. So since f prime is less than 0 on, let's look at the intervals here. The first derivative is negative on the interval 0 to 4 and 4 to 6. Zero, 0 to 4, 4 to 6. And f is continuous, so f is decreasing on the interval 0 to 6. Okay, so part B, we want to identify the critical numbers of f, if any, and determine whether each critical number is relative max, relative min, or neither. So if we look at the sign chart again, critical numbers occur when the derivative is 0 or undefined. Well, the derivative is 0 at x equals 0, and it's undefined at x equals 6. So critical numbers at x equals 0 and x equals 6. Okay. Um, now we can analyze the critical number at x equals 0. We could use the first or second derivative test, but at x equals 0, since we have a table of values here, we can use the second derivative test because at x equals 0, the derivative is 0, critical number, and the second derivative is negative, concave down, means you're at a relative max. So at x equals 0, f prime equals 0, f double prime is less than 0, so f is, let me just write it down here, f has a relative max at x equals 0. Okay. The other critical number that we have um, is at x equals 6. So at x equals 6, if we look at our graph or table here, the derivative doesn't exist, the second derivative doesn't exist. So we can't use the second derivative test, but we can use the first derivative test because the first derivative changes from negative to positive at x equals 6, and the function exists there, so we know we have another, we have a relative min. So f prime changes from negative to positive at x equals 6. So f has a relative min at x equals 6. All right, and then we're going to go on to answer the next question. Determine the intervals where f is concave up or concave down. Okay, so concavity, um, we're going to look at the second derivative. Now, if we notice, the second derivative is always negative. So the function is always concave down. Um, so the function's concave down all the time, except at x equals 6 because the second derivative doesn't exist there. So f double prime is negative on the intervals -4 to 6 and 6 to 7. And so by the test for concavity, f is concave down on the intervals -4 to 6 and 6 to 7. Okay. Also, this kind of gives us part D, which asks for inflection points. There's no points of inflection since f double prime never changes sign. Okay. And then E, we want to use the results to graph the function. Okay, so we want to sketch the graph of the function. Now we know that the interval that the function exists on goes from -4 out to 7. Okay. Now we just go from the table and figure this information out. We can pick off some important points. F of -4 is 0, -2 is 3, 0, 4, 4, 0, 6, -5, 7, -4. I would plot those first to start getting an idea. So -4, 0 was our first one. -2, 3 was our next one. 0, 4 was our next point. 4, 0 was another point. And then 7, -4 was our last one right there. Okay. Then the function was increasing from, oh, and we also had 6 comma 5, negative 5 rather. Forgot that one. So we know the function was increasing on the interval -4 to 0 and concave down on that interval. So we want to make it look like a frown. 0, x equals 0 was a relative max, and then the derivative changed sign. So now the function's got to be decreasing and still concave down. Remember, it was concave down all the time. So decreased through the point at x equals 4. And then at x equals 6, the first and second derivative were undefined. So there's not going to be a tangent line or a point of inflection. And then the function changed to back to increasing, but still concave down. So we want to draw that last little piece with a frown. Okay, so that's it for this video. Hope that was helpful to you. And you guys take care.